All right, welcome back to some examples of linearization. And we're going to look at the function square root of 1 plus x. And of course, we know that the square root of 1 plus x looks like this. And we're going to approximate the square root of 1.02. So we're going to approximate this value right here. And yes. All right. So let's take a look. First of all, we know that a is equal to 0 because we're told x equals 0. F of a equals the square root of 1, which is 1. F prime of x, the derivative, is 1/2 times 1 plus x to the negative 1/2, which means 1/2 root 1 plus x. So f prime of 0 is going to just be 1/2. So our linearization, L of x equals, well, our slope is 1/2, x minus 0 plus our y value, which is 1, and we just get 1/2 x plus 1. So our approximation, the square root of 1.02, we know that x is equal to 0.02, which means that L of L of 0.02 is equal to 1.01. So there we go. The square root of 1.02 is approximately 1.01. Now, how accurate is this? Let's find out. The square root of 1.02 is actually equal to 1.00995049 to the limits of accuracy of my calculator screen. And here's how we find the error. Well, error equals the absolute value of the difference between the two numbers. So the absolute value of 1.01 minus 1.0099 ... And what we get is 4.95 times 10 to the negative 5th. And the way we report this is that our error is less than, it should be less than 10 to the negative 4. Something times 10 to the negative 5 is less than 10 to the negative 4. That's pretty darn accurate. 0.0001 accuracy. Is that right? 0.023. Yeah. Less than 0.0001 error. Not too bad. Why don't you guys in my classes go ahead and do exercise 1. And when you're done with that, come back and we'll continue with the next example. All right, so our next example, f of x, example 2. I want to linearize the function cosine of x near or at x equals pi over 2 in order to approximate the cosine of 1.75. So what do I need? Well, I've got a equals pi over 2. F of pi over 2 will give me cosine of pi over 2, which is 0. The derivative of cosine is negative sine, which means the derivative at pi over 2 is negative 1, which means that my linearization is negative x minus pi over 2 plus 0, which means that my linearization is negative x plus pi over 2. So, what is the cosine of 1.75? Well, my linearization says But this is negative 1.75 plus pi over 2. And if I type that into my calculator, I get negative 0.179203673 Going a little crazy on the decimals because I want my error to be relatively accurate. How accurate is this? Well, cosine of 1.75, don't forget to put your calculator in radians, is actually negative 0.1782460. Wait, what? Gah. 460556. Error is the absolute value of the difference between the two. And when I take the difference and find the absolute value, I get 9.576 times 10 to the negative 4, which means that my error is less than 10 to the negative 3. Not too shabby. And so my approximation of cosine near x equals pi over 2 is just negative x plus pi over 2. All right. For my students, why don't you go ahead and do exercise 3 in, exercise 5 in the book. When you're done with that, come back and we'll have one more example. All right, welcome back to example 3. And the linearization of the square root of 1 plus x that we did earlier is actually a specific version of a rule. And here's the rule that 1 plus x to the k is approximately equal to 1 plus kx. Now, we did square root, which is a half. We came up with 1 plus 1/2, our value of x. But this is actually true for any power of 1 plus x. So let's look at a couple examples. First off, the cube root of 1 minus x. Well, let's rewrite this as 1 plus x to the power of k. And what we get is we get 1 plus negative x to the 1/3, which means that we can approximate this as 1 minus 1/3 x. Let's try it. The cube root of 0.99. This is 1 plus negative 0.01 to the 1/3, which means that this is approximately 1 minus 1/3 of 0.01. And that is 0.9966666. It doesn't matter. The cube root of 0.99 is actually 0.9966554,934. And as you can see, my error starts here in the 5th decimal. So my error is going to be less than 10 to the negative 4. Let's do another one. 1 over 1 minus x. Notice that the key to this is to write this as 1 plus something to the power of k, which means that I now know that this is approximately 1 plus k, negative 1, times the something, which is negative x. This ends up being 1 plus x. So if I want to find the value of 1 over 0.99, I could rewrite this as 1 over 1 minus 0.01. Well, that's 1 plus negative 0.01 to the negative 1. And this is approximately 1 plus 0.01, which is 1.01. So let's type it in. 1 over 0.99 into our calculators is equal to 1.01010101. And you probably realize that goes on forever. Notice that we're accurate to the 4th decimal place. All right, next example. Square root of 1 plus 5x to the 4th. Notice that they're getting more complicated. This is 1 plus 5x to the 4th to the 1/2. So there's my k, 1/2. And there's my something that I'm adding. So my linear approximation is 1 plus 1/2 of my something. So let's find the square root of 1.0005. Well, this is x equal to 0.1. K, again, is equal to 1/2. And we can approximate this as 1 plus x. One plus k times, k times x. And so this is approximately 1.05. Oh, wow, I completely messed that one up. Okay, starting that over again. One plus k times 5x to the 4th, which is actually 1.00025. This is, I did the same thing I was about to warn you against, is making sure that this has to be the something, not just x. And then I went ahead and typed it in because I was looking back and forth between my notes and my screen. So what's the actual square root of 1.0005? Well, typing that into my calculator, I get 1.000249969. And notice that rounded, it's accurate to about there. So we're talking 1, 2, 3, 4, 5, almost 6 decimal places. And you could calculate the error again by taking the absolute value of the difference. All right. I am going to tell you, my class, to go ahead and do exercise 9 in your book. I'm going to stop this video. I do have some more examples of linearization. I don't want to make the videos too long, and I think this one has gone as long as it needs to. Let's quickly recap. Linearization, L of x, is the derivative at a times x minus a plus f of a. That's just a point slope form for a close to some value, or for x close to a. And it looks like I need to run because I've got another class coming in. I will come back with more examples and more recap in the next video.